All right, in this video, we're going to see how the second derivative is going to tell us some information about the graph of a function. This is going to help us figure out things called points of concavity. So to sort of show the motivation here, let's take a look at a nice smooth graph. This is the same one that we've been looking at for the past couple of videos. I'm going to imagine a tangent line just sort of traveling along this graph. So this green tangent line, it looks like, if we go back, it had a steep slope, and then the slope decreased, went to zero, went down, kept going down, and then the slope of that tangent line started to actually go up, and then flat, and then up, and then up. So I want to focus on here, where the tangent line was negative, or had a negative slope. It went more negative, but then the slope started to go back in the positive direction. So slope was negative, decreased, but then started to increase. That point right there where we changed that value of the derivative, or the increasing or decreasing of the derivative, is what we call a point of concavity. So this is where the curvature of your graph is going to change. If you look to the left of that blue point, it looks like your graph is facing down, and then to the right of that blue point, your graph is facing up, rather. So we call this concavity. So here's a nice, beautiful sketch I made in Microsoft Paint. CD for concave down, and then CU for concave up. So going back to that graph, looks like we have concave down, and then after the blue point, we have concave up. We changed that concavity, so this blue point is what we call a point of inflection. The way we find those is finding when our derivative is going to change from increasing to decreasing, or decreasing to increasing. So you might wonder, how can I tell when my derivative is changing from increase to decrease or decrease to increase? Well, it's similar to determining when your function is changing from one to the other. If your second derivative is positive, that means your first derivative is increasing at that point. If your second derivative is negative, that means your first derivative is decreasing at that point. Another way to say that is positive second derivative means concave up at that point. Negative second derivative means concave down at that point. So this is a lot of repeat from when we were doing the first derivative test to find relative extrema. It's essentially the same process. So I'm going to bring that up. This is our first derivative test to find relative extrema. It's essentially the same process. The only difference is we're doing this with our first and second derivative rather than our function and our first derivative. So instead of finding critical numbers of f, we're going to find critical numbers of f prime. Instead of doing a sign analysis of f prime, we're doing a sign analysis of f double prime. And instead of making conclusions about extrema, we're making conclusions about points of inflection. So it's going to work essentially the same. You just have to take another derivative and then do the sign analysis with that. Also, you'll still want to make sure that you're on your graph. You want to make sure that you don't have a hole or some point of discontinuity at that critical number for f prime. Okay, so basically same thing, just added up a level of derivatives. Another thing that has to do with second derivatives is something called the second derivative test. So this is an alternative to the first derivative test. It's used to do the same exact thing to find relative extrema. What we do is we find the critical numbers of our function, and then we also find our second derivative, and then we plug those critical numbers into that second derivative. That'll tell us what the concavity is. So obviously, if we are concave down, but we have a horizontal tangent or an undefined derivative, that means we're going to have a relative max. So if I go back to those pictures here, here on the left I have concave down. You can kind of imagine if I was to make a horizontal tangent at that vertex, yeah, I've got a maximum there. So concave down, but derivative of zero. So first derivative of zero, second derivative negative, concave down. And then on the right-hand side, first derivative of zero at that vertex, but then second derivative positive means I have a minimum. So going back to those steps there, this is the second derivative test. Just to show a quick example of how that would work out, this is the same example we used for the first derivative test. So if you want to try the second derivative test, go ahead and do it. Pause that video, and then here in about 2 seconds, I'm going to show you the second derivative test. The air conditioning is getting loud in here, so hopefully it's not all fuzzy on this video. Sorry if the audio gets all weird. But here's my first derivative. Here are the zeros of that first derivative, so those are my critical numbers. And then here's my second derivative. And I went ahead and plugged in those numbers to my second derivative. And I notice at 0, I have a negative second derivative, so that's concave down. At 1, I have a positive second derivative, so that's concave up. So what that's going to tell me, at 0, I'm going to have a maximum. So f of 0 equals 0 is a relative maximum, just like first derivative test. And then at 1, I have a relative minimum. This should give you plenty of info to tackle those questions on Schoology.